All right,
And then there's some
started. Welcome back.
For speed only. So it's like,
Big group today. Let's see. You guys are here, so that's good. What?
I said, hold on. Yeah, me too.
It's about as far as my Spanish goes. All right, so last time we stopped, we were talking about kind of taking a balanced equation and then calculating how many of one you need given a certain amount of another, dealing with that in moles. And today we're going to extend that just a little bit, one step more, to also look at the actual gram quantities, because ultimately we want to be able to do this with something that we want to do in lab, which is measure things in lab in grams, figure out, okay, if I want to react carbon and sulfur dioxide, how many grams of this do I need? How many grams of this do I need to actually make that work? And then how many grams of the product do I form? So this is what is going to help us calculate that kind of stuff. And it's a big part of not just chemistry, but any kind of work where you're dealing in calculating in different units, counting versus weighing or measuring by volume. Things like measuring out medications, that kind of stuff can come into this as well. So we'll spend a little bit of time on this. We're pretty much going to do all today just working on this one type of a skill. And then we'll be done with chapter 7. So we'll have a quiz on Tuesday. So please keep working on the chapter 7 homework. Make sure you can do that all right before Tuesday. So let's try it. All right. Ammonia, which is NH3, reacts with oxygen gas to form nitrogen gas and water. How many grams of oxygen are needed to react with 13.6 grams of ammonia, NH3. So this is the type of question that we're interested in answering now. Ammonia reacts with oxygen gas, does some reaction. How many grams of oxygen do we need to react with 13.6 grams of ammonia? So the first thing we need here is we need to know what ratio these things are going to react in. Is it 1-to-1? Is it 2-to-1? Is it 3-to-2? What actual molar ratio do we need? How do we find that? Yeah, we need a balanced chemical equation. So see if you can write a balanced chemical equation for that sentence, and then we'll look at it together and see how you did. Because the first step of this, if you want to have any chance of these problems, you got to be able to write a balanced chemical equation first. So try to write that balanced equation on your own now and see how it goes. When it looks like people stop rating, I'll go on. Go ahead. See if you can get the equations. All right, let's get some equations. So what are the reactants in chemical formulas? We're going to start with NH3. What's the other reactant? Oxygen. How do we write that formula?
O2.
O2, yeah. So we got to remember that's one of those diatomic gases and make sure that it's O2 and not just O, or the reaction isn't going to balance properly. The equation won't balance properly. All right, then what are the products? N and 2 is nitrogen gas. Right, again, one of those diatomic gases. And then water. Anybody know water, hopefully? H2O. And we could list the states here also. I think all of these are gases, but we'll just leave it like that for now. So is this balanced? It's not. All right, let's do an atom inventory and see if we can get it balanced. We've got 1 nitrogen, 3 hydrogens, and 2 oxygens over here. 2 nitrogen, 2 hydrogen, and 1 oxygen over here. All right. It doesn't really matter where you start. I'm going to start with, let's say I don't know, what did you start with? The nitrogens? Oxygen? Hydrogen? So everybody started somewhere different? Okay. So we'll start with, I guess we'll start in the middle of the time. We'll start with hydrogen. We got 3 on the left and 2 on the right. So how do we bring those into balance? Same way we kind of balance with those formulas when we have a 2 plus and a 3 minus. We need 2 of these, which makes 6 total hydrogens, and also makes 2 nitrogens. And then 3 of these, which will make 6 hydrogens, and that also changes our oxygen. Okay. So now our nitrogens and hydrogens are in balance, but the oxygens are not in balance, and we have one of these issues where we've got 3 on the right, but we can only balance in even numbers on the left. You see that? So what do we do? Yeah, we're going to double everything so that one is no longer an issue. So instead of 2 here, we're going to make this 4. And that's going to change this to 4 and this to 12. And then instead of 3, we're going to make 6, which gives us 12 hydrogen and 6 oxygen. Now we have 6 oxygen on the left, or on the right, 2 on the left, so we can make 6 on the left by putting a 3 here. And now everything should be balanced.
No, nitrogen.
Oh, nitrogen is still not balanced. Thank you. 4 on the left, 2 on the right, and 2 here. See, that was a test. I totally knew. All right. Good. Balanced equation. Now we can go on. So before we talked about how we would measure moles. So if it said 13.6 moles of NH3, we would say 13.6 moles times that molar ratio of 3 to 4, and then get our answer for the moles. But now we don't have moles, we have grams, and we're asked for grams of oxygen. So what do we need to do beyond what we did before? How are we going to be able to get from grams to moles? Ideas? Maybe? We're going to use that idea of the molar mass, or the molecular weight. So how much does 1 mole of a particular substance weigh? Then we'll know how many moles we have, and then we can do that ratio we did before. So we can set this all up in one line, just like other conversion problems. Most people find that to be easiest. We'll take the 13.6 grams of ammonia, and we'll set up a little plan, just like we did with the unit conversions. We're going to go grams of ammonia to moles of ammonia to moles of oxygen using the ratio in the equation, and then finally 2 grams of oxygen. And that little system is how we're going to do it every time in any equation. So this is a little bit of a tough problem to do, but the good news is it's always the same. And when we look at these types of problems, we're always going to do the same thing. All right, so first we're going to go grams of ammonia to moles of ammonia. So grams of ammonia to moles of ammonia. And we'll get the numbers in there later. Then we're going to use the quantities in the equation to go from moles of ammonia to moles of oxygen. And then we're going to find a way to go from moles of oxygen to grams of oxygen. That way, grams of ammonia cancels. I won't draw lines just yet, but grams of ammonia cancel, moles of ammonia cancel, moles of oxygen cancel, and we're left with grams of oxygen as our answer, which is what the question asks for. How many grams of oxygen are needed? All right, now that all the units are set up, let's fill in the blanks and let's fill in the actual numbers. So how do we know the relationship between grams of ammonia and moles of ammonia? That first fraction. How do we know how many grams of ammonia are in a mole or how many moles are in a gram? Yeah. Right. Well, close. We are going to use those masses, but that's the mass in 1 mole, so we don't actually need that other number. Yeah. So NH3, N is 14, and each H is 1. So that's 14 plus 1 plus 1 plus 1 is 17. You see that? So that means that for ammonia, there are 17 grams in 1 mole.
How did you get that?
I looked at the periodic table for the different masses. Ammonia is NH3. So we need 1 N, which is 14. And then 2 H's, each of them is 1. Or 3 H's, each of them is 1. So that's 17. All right, so for the next fraction, we're looking for the relationship between moles of oxygen and moles of ammonia. And we get that from the chemical equation. Just like we did on Tuesday, that's the part that's the exact same as Tuesday. We have 3 from the equation for O2, and we have 4 for NH3. And then our final fraction is going to be the molar mass of oxygen. How many grams of oxygen are in a mole? Well, close. It's 16 per atom,
32.
but it's 32 because it's an O2 molecule. It's not just O atoms. So we filled in all the numbers now. Our units all cancel, and we can calculate it. So get my calculator up here, and we're going to go 13.6 divided by, well, I don't know how you like to do it, but you remember you multiply everything on the top, divide everything on the bottom. It doesn't matter what order you do that in. So we can go 13.6 divided by 17 times 3 divided by 4 times 32. And I get 19.2 grams of oxygen as the amount of oxygen that would react. So if we were setting this reaction up in the lab, we would know, okay, I need 13.6 grams of ammonia, and I need 19.2 grams of oxygen. I can react those and make my products. Think you can do that? All right, let's try. Same problem, same equation, but I'm going to ask something slightly different. So I'll leave that equation up there. Now, instead of asking how much reacts with a certain amount of oxygen, the question is, how many grams of nitrogen can be produced when 6.50 grams of oxygen reacts? So the question looks a little bit different. We're now asking about one of the products. We're asking how many grams of nitrogen can be produced when we have a certain amount of oxygen? A little bit different question, but we solve it the exact same way. So you set up the equation the same, but instead of looking at the relationship between ammonia and oxygen, we're looking at the relationship between oxygen and nitrogen in the equation. So you can use the exact same setup, just substitute ammonia for oxygen and oxygen for nitrogen, because that's what's being asked about. So try that, see if you can do that, and then we'll look at it together. So I put up the little plan there, just like we had before, our map. We're given grams of oxygen. So we're going to go grams of oxygen to moles of oxygen, then to moles of nitrogen, then to grams of nitrogen. So set it up in the same way and see if you can solve that. No, pretty good. All right, so to show you how similar this is, I'm actually going to just copy and paste our calculation from before. Go ahead and keep working on your own, but we're going to set everything up the same, just change the numbers as this problem asks for. So. So I changed my units around now. You see it starts with oxygen, which is what's given, and we end up with nitrogen. So we calculate the new molar masses for oxygen and nitrogen. And the new molar ratio from the equation tells us, I'll keep the colors here, 3 to 2. Good? So again, as I said, it's the exact same thing. We're just changing the numbers around, and we can calculate the amount of nitrogen that we would make in a reaction. So let's calculate it. 6.5 divided by 32 times 2 divided by 3 times 28, 3.79. that's grams of nitrogen. So is that what you got? From the equation, the balanced equation says 3 of these for 2 of these. Yeah, those are the coefficients from the balanced equation, those numbers that go out in front. All right, great. So a couple things about this. One, you'll notice that there's a lot of places to potentially go wrong in this. You could calculate a molar mass wrong. You could mess your units up and accidentally flip one. You could not have the equation balanced properly. So when you're working out a problem like this, especially in the context of this class, like on a quiz or on an exam, make sure you show your work very well. Because if you do have a little mistake somewhere, I'll still give you almost all the points if you set everything up properly. But if I just see like a random number there and it's wrong, I don't know why it's wrong. I don't know if it's a little mistake or a big mistake. So, so please always kind of write this out like this. Keeps you clear and it keeps me clear when I'm looking at it. Make sure also when you label your units, not only do you say grams or moles, but what grams or moles are you talking about? Because obviously it changes throughout this equation. So if you only have G or MOL and you don't have the actual chemical symbol of what you're talking about, you could confuse yourself and get a little bit mixed up in there. So make sure you're always following that. It's a really powerful calculation because it tells us that all we need to know is one quantity of the whole chemical reaction. If we have a balanced equation, we only need to know the quantity of one thing, and we can find all the other ones. All right. So let me show you an example problem from the book, and there's a bunch of them in here. So we will look at them. Let me copy this over. And this is kind of the whole problem, what the whole thing would look like when you'd see it. So this one, I want you to work together with somebody around you and see if you can come up with this whole thing. You'll notice there are a couple issues in this one. Solid lead sulfide, lead 2 sulfide ore burns in oxygen gas. The products are solid lead 2 oxide and sulfur dioxide gas. So you're given the reactants and products in sentence form. You have to write down the chemical formulas, balance the chemical equation, and then solve this problem, which is much like what we've just been working on. How many grams of oxygen are required to react with 30 grams of lead sulfide? So you got to be able to write the chemical formulas, balance the equation, and then solve the problem. So work together and see if you can do this. Oh yeah, what is lead?
No, maybe what's lead sulfide ore?
Oh, ore just means like the rock that you get it from. It doesn't have a chemical meaning. If you don't know the name of something or the symbol for something or the charge of something, ask around and they're working together. But ultimately, you want to be able to do this on Tuesday. Lead is Pb, if you didn't know that. You will have a periodic table on Tuesday.
Which means the podium side is supposed to be SO2.
Right.
But S is -2. Is
But that's not, that's only an
Oh,
ionic
okay,
compound,
okay.
it's minus 2.
Okay.
But the electron don't,
okay.
it's not, doesn't have a charge. All right, I know you're still working on it, but let's, at least for those of you who are really stuck at the beginning, who has a nice balanced equation for this one? You feel at least 50% okay about your balanced equation? Few people? Somebody volunteer to come up and put it on the thing for everybody?
It's not balanced, just wait. It's not
Okay.
balanced.
Anybody got a good balanced one?
I have a
Anybody?
Martial value or?
No, come up and draw it.
Can I try? I can
Yeah.
But it's not balanced.
Okay, that's fine. Let's answer it. Thanks.
What about this?
Really? Sure.
No.
What color do you want to do? What color do you want?
I don't know. Blue. Okay. You can write it here. Great. Ooh, I feel myself like a teacher.
There you go.
Sorry, I'm not an artist. Yeah. Okay. So, Laura's But wait a second, then it's gonna be here if it's 3 and it's 2, it's gonna be 6. And here it's 2 and it's 2, it's gonna be 4.
Yeah, but-
Okay, yeah, I got it.
So you good? Agree? Good, same? All right, so yeah, I think this looks good. Couple nice things about the balancing of equations. Obviously, it takes practice. You got to do it a bunch. You got to work on your homework and really, even if you kind of understand it, you got to just practice it. But the nice thing about it is you always know if you're right or not, because you can always count it up and see if it matches. And if it matches, you're right. If it doesn't, you're not. So in this case, we've got 2 lead on the left, 2 lead on the right, 2 sulfur on the left, 2 sulfur on the right, 6 oxygen on the left, and 6 oxygen on the right, 2 from here and 4 from there. So those match up, so that must be balanced. The other potential problem that comes up in writing these equations is writing the formulas for the compounds properly. Sometimes this makes the equation not be able to be balanced if you mess it up. Sometimes it can still balance, but then it's wrong. You have the wrong number. So how did you know that it was PBS and not PB2S or PBS2 or something like that?
But it's just
Yeah, so the charge lead 2 sulfide, lead with the 2 in parentheses, means that it's a 2+ ion or a +2 ion. So if it's a +2 ion, we know sulfide being in row or column 6 makes a 2- ion. So you've got 2+, 2-, one of each makes 0. So you just stick them together and make a compound. If you're still not great with making those compounds, please go back to chapter 6 and practice that, because that's a big part of this. You have to be able to build the compounds to then make the equation, and you have to be able to make the balanced equation to then do the calculations. So see, it kind of all fits together. It all builds on everything else. All right, so we've got an equation. So those of you who didn't quite have the equation right or didn't quite get to this point, now you have a balanced equation. See if you can go on and do that calculation. So this is our roadmap as we did before. We start with the grams of lead sulfide, then get moles of oxygen from the equation, and then grams of oxygen. I'll write that out here. What'd you get for the mass of lead sulfide?
230.
And then from the equation, we can see that there are 3 of these for 2 of these. And then oxygen is 32. Okay. Get 6.03 grams of oxygen?
Yes.
Yeah? All right, great. So there you go. Now you can imagine how many different potential spots for error there are in this type of a problem. So you got to make sure to work on each step, making the compounds from the words, making the chemical equation, balancing the chemical equation, and then setting up the calculation to figure out the masses. Okay, let's try another one. Oops.
Person is too late, so they would have to. But if it takes a separate, I mean, then you're gonna get down. Yeah, you could say that.
All right, this time we're looking at how much carbon dioxide is produced when 78, that's 78.0, point got a little moved over, grams of methanol burns. So this one even gives you less information.
So
What does it mean for something to burn? How would you set up an equation that looks like that?
we have to add oxygen and then in
Yeah.
the product we're gonna have water.
So the burning tells us that this is a combustion reaction, which means that methanol is reacting with oxygen. And what are the products of combustion reactions? Right, carbon dioxide and water. So we have to set up the equation that way. And so in this kind of a question, not only do we not have all of our formulas given to us, but we don't even have the reaction given to us. We have to go back and look at our types of reactions and realize, oh, this is a combustion reaction. And we know that combustion reactions mean reacting with oxygen, forming carbon dioxide and water. So now that we've said that, see if you can follow through the rest of the problem. Come up with a balanced equation again and solve for the amount of carbon dioxide that's produced. This one's a little bit of a tricky one to balance, huh? All right, if you're still working on this, great, but who's got a balanced equation? Everybody managed to actually get it balanced? Are you gonna try? Go ahead. But I'll be sitting this whole hour. Right? Might as well get up. What color do you want it to be?
I don't care.
Just leave it, whatever it was. Blue. Depends. What do you think? Is it balanced? I think so. Let's check it. We got 2 carbons on the left, 2 on the right. 8 hydrogen on the left, and 8 on the right. And then for oxygen, we've got 2 and 6 is 8, and then 4 and 4 is 8. So 8 equals that one. So when you're balancing this one, it's a little tricky because of the different components. You want to really make sure to leave the oxygen till the end. If you try to balance the oxygen before the other ones come into balance, it's not going to work out. And this is another example where I think you have to double it to get the right quantities to work out. All right. So now that we've got that, let's set up this problem if you haven't already. A little more space here. Now that we've got a balanced equation, the rest of it is the same as it was before. All right, so methanol CH3OH, carbon is 12, oxygen is 16, that's 28, and 4 hydrogens is 32. And then the equation tells us we've got 2 of these for 2 of these, so it's an even 1-to-1. And then we've got, what was that, 44? 36, yeah. No. Yes. 44, yes, per mole. Okay. Calculate it. 78 divided by 32 times 44. 107. 107.2. 107 grams of CO2. Sound good? Sounds about right. All right, let's try another one. Oh, I should note one more thing here. This idea of calculating how much you expect to produce in a reaction when given a certain amount of starting material has a name. It's called the theoretical yield. How much do you expect to yield from this reaction? The reason it's theoretical is because no reaction can really be perfect. No reaction can be so perfect that every single molecule goes from one side to the other. Most reactions have what's called an equilibrium, which means a little bit of the reaction is going backwards, just as most of it is going forwards. Other reactions are inefficient for various ways, or maybe the reaction itself is efficient, but the process, the way you actually do it with the glassware and everything, leads to some inefficiencies. You have to filter a product or something, you're going to lose some. So when you actually physically do a reaction, you can really never get the true theoretical yield, the exact amount that you calculate. So you get something called an actual yield, your yield of the reaction. And you can judge how good that is or how efficient that is based on comparing it to this theoretical yield that you calculate. So that's what that's called, if you see that come up in lab or something. All right, let's try one from lab on Tuesday. Reacting samples Remember doing this on Tuesday? Cobalt nitrate reacts with sodium hydroxide and produced this blue precipitate that you centrifuged. I think that was the blue one. It might have been the purple one. There was like one that was kind of more teal and one that was more purple. We'll call them both blue, then we can be right either way. That, I think this is one, but I can't remember. So this one, we're assuming that the reaction went to 100%, meaning that we actually got the theoretical yield. We know it's not totally possible, but let's say that we got the theoretical yield. We've filtered off that liquid, that clear liquid, and found that there was 0.328 grams of that blue precipitate. How much of each reactant was used? We can figure out how much of each thing we started with based on measuring the product, assuming that we mixed them in the correct ratio. So same kind of problem. We first need a balanced equation. And if you got through the lab, you did this balanced equation, but you may not have gotten that part yet. So you can try it again now. Cobalt nitrate reacts with sodium hydroxide. And notice I just say it forms a precipitate. I don't tell you the products. How are you going to find the products? Yeah, you do this. Yeah, you recognize that this is a double replacement reaction. You've got two ionic compounds. So they're going to switch partners. The positive ion is going to go with the other negative, and then the negative goes with the positive. So give that a try. See if you can come up with a balanced equation and a solution for how much of each reactant is used. So first balanced equation, and then go from there. Cobalt is CO. Part of the tricky part of this one is actually building those compounds, making sure that you have the right formula for cobalt nitrate, sodium hydroxide, and then the two products. as we're getting close on time here. Did anybody get a good equation for this, you think? You want me to just do this one? Okay. So for cobalt 2 nitrate, cobalt 2 tells us that it's cobalt 2 plus. And what's the formula for nitrate? And what's the charge?
1 -
Yeah, 1 minus. Make sure you know those polyatomic ions. So if we're building a compound of that, we need 1 of the cobalts and 2 of the nitrates so that they cancel out to make 0. So that's cobalt and then NO3, 2. Sodium hydroxide, NaOH. And then what's that going to produce? Yeah, we're going to switch the partners, so we should write all the ions here. So sodium plus and OH minus. So the cobalt's going to go with the hydroxide, but is it just COOH?
No,
Right, we have to rebalance it. So we have to see that hydroxide is -1. So when that goes with cobalt, we're going to need 2 hydroxides for 1 cobalt. So it's going to be COOH2. And same thing with the sodium. It's not going to be NaNO3, 2 because sodium is +1, nitrate is -1. So they're going to go together in a 1-to-1 ratio. NaNO3. All right, is that balanced? No. So we're going to need a 2 here, and a 2 here. Now we've got a balanced equation. I think. Yeah. All right, so we got a balanced equation. Now we can go on with the calculation. Now remember, don't get thrown off if the just because the quantity is something of the product rather than the reactant. Any quantity you're given, you can solve any other one the same way with the same calculation. So what is the blue precipitate? Is it cobalt hydroxide or is it sodium nitrate?
Sodium.
Why?
I don't know. I just had experience with
Just a guess.
being, precipitate.
Okay.
because we added cobalt with sodium.
Yeah, and you may not know this from a problem like this, so which is fine, but the blue precipitate is the cobalt, not the sodium. Sodium nitrate is soluble. Cobalt is very. Have you ever heard of cobalt blue? It's like a paint or a color, or like sometimes a color is named cobalt.
What's it? Flavor Mountain Dew or something.
Is it a flavor of Mountain Dew also? Okay, I hope it doesn't have actual cobalt in it because it's pretty poisonous. But yeah, cobalt used to be, probably still is used in some pigments, like for oil paints and things like that. It's a very deep, kind of recognizable blue. But as you saw in lab, cobalt can also take on other colors depending on what it's reacting with. So cobalt nitrate in solution is actually pink. Remember that this solution kind of started pinkish or red, and only when you made the hydroxide did it turn blue, or it could also turn purple with the, I think that was the phosphate. All right, so anyway, this is our precipitate. So that means that we start with 0.328 grams of cobalt hydroxide. And it says solve for each reactant. For time purposes, we'll just pick one. Which one do you want to solve for? Cobalt nitrate or the sodium hydroxide?
Well, couldn't you actually solve for one and then subtract the other?
No, because there's also, because this isn't the only product that forms. So it's true that the masses have to be equal on both sides, but we need to know how much we have of both of these things to be able to subtract it. All right, so let's do the cobalt nitrate. Oh, whoops, I wrote this wrong. I want to show you a little shortcut, if this works. when you're doing these kinds of calculations, obviously you want to know how to calculate a molar mass by adding these things up, but we've done that a bunch. You kind of know how to do that. There's a great website called Wolfram Alpha that can do some of these things. So you could type in cobalt 2 hydroxide. We don't even actually have to finish typing it, and it tells us the molecular weight is 92.9 grams per mole. So it adds it up for you. It can also be useful to find other things like physical properties, melting points, boiling points, safety information, density, that kind of stuff. So, what?
Yeah, but we can do it.
It's true, you can't do it in exams, but if you know how to do it and you just need to, you know, get through it, then yeah. Yeah. Have you seen the site before? Has anybody ever used this before? Okay. It does a lot of neat stuff with math too, but you're right, you can't use it on the exam. So. And the equation here tells us that this is a 1-to-1 ratio. And then for cobalt nitrate, did anybody come up with the mass for cobalt nitrate? 93. Are you sure?
No.
Okay. I was going to say that 121. That seems more likely. So, and let's think about that. When you add that up, remember the parentheses, this 2 outside the parentheses applies to everything inside. So you got to add up cobalt, which is 59, and then 2 nitrogens and 6 oxygens to get that total mass. And that comes up to 121. All right, so we evaluate all that. Right, 418 grams. So we must have started with 0.418 grams cobalt nitrate, assuming the reaction was complete. All right. No? Let's add it up and see. So we've got cobalt is 59, 58.9, and then there's 2 nitrogens, so that's 14 and 14, and 6 nitrogens, or 6 oxygens. So that's going to be 16. And this one doesn't do order of operations properly, so I have to do it all like this. So it should be 183, not 121. Okay. Let's check with our magic shortcut here just to make sure. Yeah, it should be 183. Yep. Okay, so that's not right. Try it again. That's not right either. 0.328 divided by 95 times 183. There we go. 0.63. Thank you. All right. Have a great weekend, and I'll see you on Tuesday for lab. We're going to do a similar experiment in lab on Tuesday to what we did this week, but instead of just kind of doing it and watching what happens, we're going to actually do these calculations for a real reaction that we do. So please practice that. We'll have the quiz and class, and then we'll go up, we'll talk a little bit more, and we'll go up and do lab. So this is going to be an important part of what we do in the near future. This stuff. Yeah. Yes. Chapter 7 stuff, yeah.